Okay, questions? Guys, questions?
I'll just kind of start with this because I know it's going to recording. So like, can you like quickly define like can you quickly summarize like how can I understand like dynamic binding polymorphism?
Quickly summarize.
Or you can put it later if you want.
Okay, so
Recording, I think that's fine.
yeah, the question really is about polymorphism and dynamic binding, right?
Yep.
Okay, since you say summarize, I'll make it very brief. Okay, of course you gotta go over the slides and see, right? Usually you got some inheritance hierarchy over here. Okay, it can be some tree over here. It can be some tree over here. Okay, so now let's say this is called A, and somewhere down in the middle you got a class called C. Okay, you got A and C. Okay, so a very typical scenario you will see is, let's say OBJ is of type A. And then you're going to say creates C and then OBJ the make, right? Because C is a descendant class of A, right? It's a very typical one. So for many design patterns that we talk about in the class, like observer, composite, also state pattern, right? Many patterns that we talk about. So the very typical case like this. Let's say we got array, which is going to be an array of, it can be linked list, can be iterable, just a collection. Let's say array of A. Okay, and then, so now if I say A at position I, assuming that I is valid index, that can be assigned to something. Okay, so now what can we assign statically? What can be the question mark? Any descendant class of A, right? Okay, good. Okay. My point is, it's only a summary, right? So I would say a very typical scenario you might see in the exam as well would be when you run a loop like this across A, for example, across A is, for example, OBJ. Okay. Let's say loop, for example. And now let me ask you this: when I say OBJ dot something, question for you, okay? So now when I say the question mark over here, what feature can I call on the question mark?
Whatever feature that's present in A and that's been implemented in like its children.
Oh, when you say children, no. Okay, let me give you a typical example. How about that, okay? Okay, be careful. I think it's worth mentioning. Okay, let's say this. If you got A over here, okay, let's say A is pointing to, let's say just two elements of the array, okay? Let me make it a little bit more concrete for you. Let's say somewhere here we got D, okay? So C and D are descendants of A, okay? So now let's say the very first element over here is of dynamic type is D. And so second element here, dynamic type is C. Let's say for A over here, we got a feature called F1. Class D, we got feature 2. And then C over here, we got feature 3.
So it'll only be feature 1.
Yeah, only be feature 1, right? So now, let's say this. Exactly, over here, OBJ will just be feature 1, right? That's the only thing you can say. But now, be careful. Dynamically, A2, for example, is pointing to a C objects. So can I say A2 dot F3? Can I say that? I cannot, right? It's a very typical example where you can know statically over here, A2, the static type is according to A, which is A. And F3 is not defined in A, it's only defined in C. What if I'm really sure it is really pointing to a C objects? Check attached, right? Like a cast. Okay? So if I'm really sure, I have to say check attached. Okay, I'm pretty sure I know how to do this. Okay, C, let's say, for example, as, let's say, C objects. Okay, let me also put A2 here. I forgot to put A2 here. Okay, it's C objects, and then you can say then, And now I can say C objects dot F3, right? Okay. Basically the cast that you would do in Java, okay? Just the same idea. Okay. Yeah, it's a very quick response to your question, but I would say you want to review the inheritance lecture just about how to do the various things, and also review all the design pattern to see how the design polymorphism and binding is being used.
Professor, can you go over visitor pattern in the open close principle, then the state pattern, and then possibly do a question like everything? Possibly do a question.
Let's do one at a time. Okay. Which one?
So visitor pattern and open close principle.
Visitor pattern and open close principle.
I'll like double dip faster. Simple that visitor pattern.
Visitor here. Okay, possibly I can do that. Okay, so now let me go back here. Okay, visitor. Okay. I believe many of you actually use the composite visitor in your project, so there should be some reasonable familiarity over there. Okay, so now let's say this. For the visitor pattern, okay, you can see for the composite over here, you got at the top, you got deferred, also you got effective. So make sure you know about the syntax for the bond diagram, right? We have been doing so many labs, right? Also your projects for that, okay? And also you got inheritance over here, okay? So now let's talk about the essence for the visitor, okay? Whenever you talk about the visitor pattern, you're really assuming that you got some structure, like a composite already. That's what you assume, okay? So you can use it. From the structure side, what you have to do is to say at the top level over here, you have something called accept, okay? The accept declare v of type visitor. That's what you do here. And then that one is deferred, and that will force every descendant class that's effective for the composite to make sure you can accept a particular visitor, okay? And the implementation of that is actually pretty standard, okay? The way you do it, for example, over here is like this. Just give you one example here. You would say do and also end. You would simply say v dot what? Any idea? V dot accept. Are you sure? Well, think about what the type is, right? V is visitor.
Visit, constant.
Yeah, exactly. Depending on what the current class is, right? Visit constant. Okay, and then over here you put current, okay? Because every visit feature is expecting some expression, the structure, okay? And then of course similarly for the addition you would say visit addition, okay? That's what you would say. Okay, the very standard operation here. I'm going to trace the code a little bit later. Okay, and then for the expression operations here, so now you got visitor here at the top, okay? And also make sure you understand why we have this particular client-supplier relation over here. Of course, you better put plus over here, okay? Basically, every time when you do your client-supplier relation, make sure you say either plus or deferred, right? Plus or star, and also give the name of the supplier name. Oh, yeah, that should be deferred. Yeah, absolutely. I agree with you. That should be deferred. Oh, no, actually, you know what? This is very similar to, remember in the iterator pattern, we say, let's say for your repository, when the repository goes to, oh, sorry, what I meant, let me give you another example. Remember in the iterator pattern, what we get is, for example, iterable something here, right? And then iterable has something called new cursor. And that one's deferred because new cursor is simply of type iteration cursor, right? That's the same idea. So you're simply hinting that at the expression level, the accept is simply not implemented. That's why you put a star over there. Yeah. Mhm.
So, with respect to like open and close principle here with the visitor,
Yeah, we'll get to open and close in just a moment. Yeah, bear with me. Yeah.
Since we draw that client-supplier relationship, Professor, if we, let's say, had a collection of visitors being supplied from the visitor to the client, which is, let's say, composite class, how would you draw the diagram? Like, how would you draw the actual like the annotation for the relationship? What I'm trying to ask is, let's say, in the iterator pattern, right? When we have a collection that's being supplied to the client, we often write dot dot right in the brackets to
Uh-huh.
know that that's the client. So can you clarify that? Just so
That's a little bit aside. Okay. I'll come back to this diagram in just a moment. Okay.
we're drawing
Okay, let me just do this guy here. Let's say this. If I got a class called A, and then over here, let's say I got something called surface, for example. Let's say it's an array of B. Okay. Assuming that I have a class over here called B. Of course, there might be something else over here. Okay, let's just focus on this. So now, how do you draw the client-supply label for this? Okay. Also, there's something you should really review for your bound slides, right? That's also something we made available to you previously in the slides. So you got different options. Okay. Either you can say the following. Okay. You can either choose to emphasize on the array part, or you can choose to emphasize on the B part, right? Apparently, this you can think about. This is one supplier. This is just another supplier. Different suppliers, right? So you got two different suppliers over here. So now, how do you actually draw the diagram? You got two options, right? Depending on how you were asked, but I'll just say in general. So there are two ways to draw this diagram over here. Okay, number one, let's say we want to focus more on the array, okay? Which means we want to show the array in the other part. What we can do is, first of all, you can draw A over here, okay? And then you want to focus on the array. So now you can say array. Remember, array or any collection class, they are generic. So that means you want to instantiate the generic parameter. In this case, that will be array of B. Okay? So now in this class name over here, you say that. Of course, according to this, both of them are effective. So I'll put plus over here. And now I'm going to have a client-supplier relation over here. Okay? So now it's going to be just surface. Right? Okay? Plus is implemented maybe. That's one way to go. You are more focused. You are more showing that the supplier is actually an array where every element is B. That's one way to go. Another way to do it is by focusing more on the B over here. Okay, let's see how we do that. So for the second one, I still have my class A over here. So now I want to show B as the target, also effective, let's say. So what I would do is I'm going to draw a client-supply relation over here. Okay. And now, what should I do? Any idea? Any suggestion? What should I put? I definitely should put surface, right? That's a name. Okay. And then, what should I put over here? Array. And then, okay, if I put array here, I agree with you. But now, what should I put over here, right? Dot, dot. Yeah, okay. If you only put B here, that's partially correct. Okay, I would say you can get partial marks for sure. Okay, but the syntax tells you, since you know it's pointing to B, so there's no need to actually mention B again. So you can just say dot dot. Okay. Yes. Yes, you should. Absolutely. I agree with you. Yes, thank you.
What if, like in the iterator pattern, we have more than one collection supplied from the same client to the same client from the same supplier? In that case, can we kind of be lazy
I would say you want to restrict every client-supply relation to a particular attribute or declaration. Yeah, just one. So I would say depends. So maybe for that one, you can refer to the iterator pattern diagram over there. Yeah. Okay. Guys, are we okay with this? Okay, I think that was important. Okay, it's good that you ask. Okay, so let me go back to the visitor. So the plus here, yes, is effective. Correct. 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 Yes. Yeah, so deferred class means it's at least one feature that's deferred, which means unimplemented. Yeah. Effective class means every feature is implemented. All right. Yes.
So what if we have a complicated data structure, such as a hash table, and we have two things inside the bracket?
Oh, I see what you mean. Okay, sure. I think that's a good question. Let's say you got class over here, and then you got book. Okay, and then you got n here. Let's say implementation. Let's say hash table over here. Let's say it's a birthday book. So you're going to be birthday, and this key will be string name. Okay, so now I would say in this case, again, you got three different options. Okay, the first option is going to be very similar to the case of array of B. Okay, very similar. Okay, in that case, you can simply draw. Okay, first of all, the book, which is effective, as presumably, and then you're simply going to have a client supplier over here. Let's say implementation, which is effective, and then that one is going to be hash table. Okay, I'm just going to write a short hash table, and then date and also string. Okay, of course, you're going to spell it out properly. Okay, that's one way to go. Oh, of course, this one should be effective, right? So I would suggest when you actually do your exam question, if that's about drawing bond diagram, when you double check your answer, make sure for every class you say it's either effective or deferred. For every client supply label, also to say effective or deferred, right? Just make sure. Right.
So you said the question, if the question asks, focus on either the data structure or focus on the client. So
Yeah, I would say if the question actually tells you, then you will know what to draw. If the question doesn't say, you have the freedom.
then the question would say focus on the collection or focus on the data structure.
Yeah, you'll be clear enough in the question. Okay, so another option here is to say, you can say book. So now, here's the thing. So since we got date and we got string, so now we want to decide whether we want to focus on date or string. Because whenever you use dot dot, right, the dot dot only refers to the class that's being pointed to. You cannot point to the two classes simultaneously, right? So now, let me give you one example. Let's say book is still deferred, effective. And then what I would say is something like here, okay? Let's say I want to focus on date, okay? Let's say. So what I can say is, I can say implementation over here, effective, of course, is going to be hash table, okay? And then I'll say dot dot. And then I'll put string here. Which means you shouldn't put more than one dot dot in a single label. Okay, and then over here you can have effective date. Okay.
So if I cannot do int is the hash table dot dot because like there is two, I can report to two things at once, right?
Yeah, you cannot.
Oh,
Yeah.
got it.
True. Okay. Okay, that's just an aside about drawing bond diagram. Okay, you should really go over the whole slides and then just see everything else. Okay. Let me go back to visitor quickly. Okay, so now in the visitor, okay, so now for the visitor, you got at the top, and also you got different effective class descendants over here, right? And how many visit feature you should have depends on how many classes you have at the composite level, right? So now over here you can see we got basically constant and we got addition. So 2 effective is descendants for composite. So that means you should have visit constant and also visit addition. Okay, that's how you figure how many you should have. Okay, open close principle. So anybody wants to answer what's open close principle? If there's a definition question.
That like if you have that your implementation of how you implement the code should be closed, but you should always have it open to extension, so that if you wanted to extend and add on whatever you've already implemented, you're free to do so. But the client should not be able to close the implementation.
Yeah, so here you're saying that the implementation should always be closed. I would say it's actually true, but not the whole truth. How about that? Okay, I would say like this.
The client shouldn't have to care.
Yeah, think about the closed part is the part the client shouldn't care. Okay, so every time you think about open close principle, think about information hiding at the same time. Okay, so that's a diagram I like to draw every time. Think about this guy here is your whole system. Okay, somehow you have to hide certain part that's closed. Also reveal certain part that's opened. Okay, so what you should do is over here, you can think about this part here. This part is open part, which means they're subject to change. Oh, sorry. Yeah, sorry about that. I meant the opposite. This part is the interface is something that shouldn't change often. Okay, so this let me just change the color here, so that'll be a little bit better. Okay, I think that's good. First of all, this is public, which means they should be stable, which means they should not be subject to change, not to be changed often. Okay, that's the open part. Sorry, that's the closed part. Public, and this is a closed part. Okay. On the other hand, over here, this guy over here, the other part of your system over here, that's more like a private. And they somehow may be unstable. Okay, subject to changes. And which means they're open to changes. Okay. So now, which part should be open, which part should be closed is completely up to your design decision. Okay, presumably you document it in your report, right? We're going to read it. Yes. No, actually, open part simply means it's open to changes. Think about, okay, think in this way. If, okay, you know what? Somehow maybe public, private. You know what? Let me try to adjust this a little bit. Let me not to really confuse you by just public or private. Okay? Think about stable versus unstable. Okay? Think about which part of your system should really remain stable. If they are not stable over there, like the red part, so that means they're subject to changes. What can be a open part? For example, if you go back to visitor pattern here, okay? So now, this is the visitor architecture. So now, which part should be open? The operation, right? Why should that be open? It's simply because if I simply add a new operation over here, there's a single place I'm going to add things over here. So that part is open, okay? On the other hand, if somehow I try to change something that's closed, for example, if I'm trying to add a new class over here, let's say class C, okay? Accordingly, I should really say visit C over here, right, etc. And then I should really add that feature there for here, here, and here. So there's multiple places I'm trying to make. So that's affecting more parts than necessary. Okay. Yeah. Open close principle. Open close principle basically talk about which part should be open. The open part should be somehow unstable and subject to changes. So this is like a visitor descendants. So they are open to changes. On the other hand, once you decide which part should be closed, like the stable part, and that part is really like how you decide for the composite structure. They should be closed. Yeah, that's how you link. Yeah. Mm-hmm. Yes.
Professor, do you mind if I can ask a question about symmetry pattern on that note?
Not yet. We will get there. Chelsea. Open to changes by the supplier, yes. Mm-hmm. Correct. Yes. All right. So open is unstable simply because it's open for changes, right? So that means you might change the open part quite often. So that means it's unstable. Well, it's more. You can change that more often. That's okay. On the other hand, if you find that, given that this particular part is actually closed, that means you shouldn't really change that often. If you change that often, that means your open and close decision is actually wrong in the beginning. Wrong. Mm-hmm. Yes. Mm-hmm. No, not compilation error. Nothing to do with compilation. I'm saying that if you decide this part of your system should be closed, you shouldn't change that often. If you change that often, that means the original design decision that should be closed is inappropriate. Okay, so now I think we cover also the visitor here. Okay, the next one will be double dispatch. Okay. Okay, so now, here, before we get to this particular line, okay, when we say some composite over here, some composite, and then you say accept, right, and then some visitor. Double dispatch actually happens right here, every time you try to do accept. Okay, double dispatch simply means dynamic binding is going to occur twice, one followed by another one. Okay, depending on how many accept you might have different number of double dispatch, right? It's more like pairs. Okay, so now before we do that, you want to make sure you're okay with building a composite tree, right? I'm sure you have done lots of exercises in the project, right? So now over here, we're simply creating a constant over here, okay? So C1. So C1 is pointing to a constant. The value is simply just 1, okay? And then we're creating another constant C2. C2 is now pointing to a constant, and the value is simply just 2, right? So these are the two base cases, okay? And then we are trying to add also addition, okay? Let's say addition here. So now it's add. Add is now pointing to an addition. And now every composite has left and right, okay? If you just look at the diagram. They got left and right, okay? So what I would do is I'm going to say left and right. So now the left is going to point to C1, and right is going to point to C2. That's exactly how you build a tree. Okay? Of course, I'm assuming a particular way of implementing the composite, but that's how you build. This is only just one simple example. Okay? Exercise for you. Exercise. Write a fragment of code which builds the following composite expression. Okay, how do you do that? Okay, there's an exercise for you. There might be, there might be not. Just so you know, to be honest with you, for now, I don't care what's on the exam. You know, I just want to think about what you should know. Okay. I would suggest you do the same thing, right? Yeah. Are you okay with this? Okay, just to build a composite. Okay. Do you need help on this, or you're fine? I can sketch a little bit. What you should do is, you should first of all create a constant for 1, create a constant for 2, and then create an addition here, which add constant and constant, okay? And then create a constant for 3, create a constant for 4, and create addition, which add 3 and 4. And then create another addition, which will add this addition is left, and this addition is right, okay? All right. Let's say we know how to do this guy here. Let's move on to the next one, okay? So now what we have is, let's say this line here, okay? We want to do add the accept v. So add is just addition. And then we got left and right, okay? And also we got evaluator here, okay? So v static type is visitor, dynamically just evaluator, okay? So now we want to know what's the evaluation result for add. Let's see what the result should be ultimately. It should be 1 plus 2, okay? How things work typically is by saying it's like a recursion. In order for me to figure out the evaluation result for the addition over here, I should really declare as many local visitors as I find necessary to handle the subtrees. You can think about, in general, this is the left subtree for the addition, right? And this is the right subtree for the addition. In this case, left subtree and right subtree, they're very simple. But of course, you might get a little bit more complicated stuff in other scenario. Okay? The left subtree over here, right subtree over here. You're going to basically create another local visitor to handle this, another local visitor to handle this. That's what you will see at the runtime. Okay? But we'll get there. Okay? So now what I would like to do now is to trace this a little bit and talk about double dispatch. Basically, think about how dynamic binding is going to happen. Okay? If I got add the accept, well, what's going to be the first dispatch? How is dynamic binding going to occur for the very first time?
Determining what the dynamic type of visitor is.
Oh, so you're talking about, let me just make sure I understood you correctly. Okay, you are suggesting the first dispatch is going to be determining what the dynamic type of V is and then do something. Are you sure? Or anybody who have a different thought? Aha, exactly, yeah, exactly. What you just suggesting was there. Yeah, there'll be a second. Think about, if you talk about V, right? You wouldn't get into V until you actually go to the body of accept. How do you know which one to go, which version of accept to go to? You gotta see what the add is, okay? Okay, so the first dispatch is going to be dynamic type of add. How do I know what the dynamic type is? Well, usually if you know how to draw the diagram and trace, you will see the box over here is addition, okay? So that means call the accept in addition. Okay, that's the first dispatch. And now if you go to the addition class, okay, so you got two versions here. Either you go to the version for constant or you go to the version for addition, either way. Okay? But now this case, because dynamic type is actually addition, so we go to the addition version. And then that one there is going to call the accept. And one thing to note over here, you can see over here the V, call by value, is going to be replaced by the V over here, okay? And the V is really pointing to some evaluator. So now we go to what you just said before, right? Okay, so now can you tell us what's gonna be the second dispatch?
So depending on the type of visitor, it's going to go to the definition of that visitor, which in this case is the evaluator, and go to the visit addition.
Yeah. Yeah, exactly. Okay, very good. So now basically you can see that this V right now, we are calling V the visit addition over here. So now, first of all, if you only look at the architecture, how many visit additions do we have? How many versions do we have statically? 3, okay? Because for each, you can see visit addition is actually a feature that's deferred over here. So that means every effective descendants should implement it, but we don't know which version it is. Do you know it? You need dynamic binding. Okay. So now let's go back there. So what you will get is to say V over here. So now dynamic type of V over here is evaluator. So now that means you're going to call the visit addition in evaluator. Okay, that's the second dispatch. The first dispatch depends on the dynamic type of the expression, the composite. The second dispatch depends on the dynamic type of the visitor. Okay? Of course, in the exam, you might be given something similar, or might be given something that's slightly different, but the principle is the same. Okay, okay, let me talk a little bit about how you can go a little bit further. Okay? So now we are going to call the visit addition over here. So now we know the visit addition. We got either version 1, that's in, oh, actually the only version we have is in the evaluator. That's the one we're going to use. Okay. So now in the evaluator, okay, we got visit addition. Okay, that's the one we're going to call. Okay. So now let me mention something very quickly. Okay. You can see over here we have evaluate left, evaluate right. So this part is really important. That's how things can work even in the complicated case. Okay, let me say again. Okay, let's say you have the composite. Let's say you got addition. In general, you got left, you got right. The left and right can be arbitrarily complicated. That's why I draw the tree like that. It can be simple or it can be complicated. The way you handle that is by declaring just another visitor. You can think about when you say evaluator visit addition. Let me just call this add. Okay. Okay, this one actually simply comes from there, right? With visit addition here. Okay, I'm just replacing it. Okay. So now what we'll end up having is as follows. You're going to get basically 2 local visitors. One is for the left subtree. The other one is for the right subtree. And then you can see that, again, each one of them will consist of another double dispatch. Right? This will be double dispatch. And this one here will just be another double dispatch. Fortunately, these two are just base cases, right? So when you evaluate, for example, the left, when you evaluate A dot left, it's simply just a constant. How do you evaluate a constant? You will simply return, I don't have it, oh, it's here, over here. When you visit the constant from the evaluator, it will simply give you the value, which is just 1, okay? Okay, and then let me say one more thing over here. So now, if you look back the diagram over here, you can think about this part here is going to be handled by, like this. Eval, oh. So add, which is this object here, right, is add, dot left, left, dot accept. And then you're going to get eval left. Eval left over here is just a temporary visitor to help you, okay? And also, similarly, you also get another one to handle the right subtree. So that'll be add dot right dot accept. And then you got eval right. So this is just another visitor to help you, right? You got 2 different helpers. Okay. It's pretty much like how you call recursion in 2011, right? How do you do, let's say, post-order traversal? You try to call the recursion on the left subtree, call the recursion on the right subtree, and then handle everything together. Right?
How does the value get updated?
The value. Okay, good. Thinking this way. So let's say this. For this particular case, the left subtree is as easy as 1. Okay, 1 and 2. Okay, 1 and 2 here, right? You can think about, because it's going to be recursive, okay? This eval left is simply just an independent visitor objects. So eval left is simply just going to point to some evaluator objects, okay, first of all. And also eval right is also pointing to another evaluator objects. So now, when I handle this case over here, it's trivial, right? It's just 1. So now it's going to set the value for this particular evaluator to be 1. Also, it's going to set a value for this particular evaluator to be 2. But now we are not done yet. You can think about what we have done so far is we have handled this part here and get some value. We have handled this part here and get some value. But what we really want to evaluate in the first place is this addition. And remember, the way we did it was by creating, remember this evaluator, right, to begin with. So we got 3 evaluators in place in this particular example. So you can think about this particular evaluator V. So V is pointing to another evaluator. So now, how do we set this value here, right? Basically, we're just going to say, upon the termination of the left subtree handling, get eval left the value, which is 1, plus whatever result that's done recursively on the right subtree from the right evaluator, which will be 2. You add it up together. Okay? So now what you will get is, over here, will simply be eval left dot value plus eval right dot value. Right? That's what you'll get. Okay. Maybe that's what you meant, right? Okay. Not so challenging programming question for you to think about. Okay, think about it. Let me go back here. Okay, what I would do is I'm going to change the definition over here a little bit. Okay, that's the evaluator over here, right? Basically, we see that every evaluator has a value. Okay, what I would do is, let's say I get rid of the local here. Okay, and now, rather than using eval left and eval right, they are not there anymore. I'll simply say current. Let's say that. Do you think it's going to work?
It will completely forget about what the left side is.
Ah, exactly. Okay. Yeah, they'll completely forget. Well, basically, you cannot keep track of the left and right, right? Think about, okay, for those of you who are a little bit confused, let me just mention that quickly, right? That's why you can think about why we need a local. Let's say addition, again, that we're trying to handle. That's the left, that's the right. So now, when you are calling this particular one, you're saying A dot left. Let's say this is A, okay? A dot left, the accept current. He's going to evaluate this particular one. Let's say you get a value of 1. So now, current dot value has been set to 1 for now. And then you're going to evaluate the right subtree over here. Let's say it happens to be 2. So now, since you're using the same evaluated current, so that means you're going to wipe out the 1 to be 2. So now you can never remember 1 and 2, right? That's why you need 2 local variables. Using current is not going to work. Yes.
Suppose you could do that for one side of the tree.
Yeah, but somehow not. Yeah, you're right. You can just do for one side, just make a local variable only, just one single local variable. But it's not. It's nice. I think it's nice to be conceptually clear. We're trying to do separately. Yeah. Yeah, it's just a very simple programming question to answer, right? Okay, that's about visitor. Yeah. Observer pattern, which part?
Specifically, like example, so there's 2 types. The first is regular observer pattern, and then it's like event-driven observer pattern, right?
Yeah, I think I would suggest any other questions you might have. I would suggest the following. So if you really want me to go over the entire thing, yeah, that will take some time, right? It might be nicer for you to point to me exactly which part of the observer you got confused. I think that'll be easier for me to answer. Yeah.
Not the observer, but specifically in regards to the single choice, single choice principle, which I wanted to ask about earlier.
Uh-huh.
So if I say to the professor that my definition of single choice principle is that when we have a piece of, like, let's say a system, right, and then we have different features of that system, we look at the number of places where we would have to make changes if we were to add a new, let's say, class in the system. That would, like, the number of places we make changes is what we would evaluate whether or not if the code stinks or not. Because if you have to make essentially changes to a lot of places and you add one class. Right?
Yeah, basically a single. Yeah.
What I'm asking, what's your definition of single choice principle?
So single choice principle, the definition I gave on the slides was here. I believe on the inheritance slides. I think we can go to, you know what? Might be easier if I simply go to the web. Yeah, single choice principle is really talking about repetition, right? So you want to make sure every time you want to make changes, there's only a single place with a minimum number of places you're going to make. Okay? Let me refer you to what you should look at. If you go to inheritance over here, I believe single choice principle is over here. Okay, over here. Okay. Basically, if you recall how we reviewed the inheritance topics, right? We try to give you the two student classes with duplicates, right? That's where the single choice principle is violated. Okay. So what's single choice principle? Okay. So now you can see when a change is needed, there should be a single place, or at least a minimum number of places, if not just one, that you should really modify. Okay? So we talk about single choice principle in many different scenarios, right? At least we talk about when we talk about inheritance, okay, about code reuse. And also we talk about single choice principle even in the visitor pattern, right? For example, if you have to change, let's say the composite site, which should be closed. In that case, you're going to modify a number of places in the visitor, right? What I meant was over here, if you recall, okay, again, the architecture diagram is really important over here. Okay, let's talk about this guy here, okay? We know that according to open-close principle for visitor pattern, this part over here should be closed, okay? So now, if I try to make a new class over here, is there a single place I need to change accordingly? Not really. Because over here, if I add a class called C, that means in the visitor class at the abstract level, I got to say visit C, first of all. That's deferred. And then for every effective classes, more than one, I need to add in this visit C. So that's multiple places, right? So that's one example where a single choice principle is violated. Okay? Also, you can also review the state pattern about single choice principle. Chelsea.
So can I ask a quick question about one solution of practice?
Sure, no problem.
For you said that had like math class and had a function that said in a balance the index has to be valid and the balance at that index of the prompts has to be completely on and not one.
You mean this one here?
Yeah, you said the solution was that you have to use and then so that for a specific reason that way a count isn't valid because it's kind of valid.
Yeah.
Could you split those two statements up into two separate solutions? You have valid index
Yeah.
and then valid.
Yeah, I see what you mean. Absolutely. Let me just do exactly what you said so everybody can understand. Okay. Okay, so now what I will do is I wonder if this might work. Let me see this. Okay, give me one moment. I'm just gonna copy that part here. Okay, good. Okay, so now that's the example here, right? So the problem for this is as follows. So now let's say we got array A, accounts. Let's say over here, if I simply give you I, such that I is not valid, for example, just -1. Okay? If I give you that, in principle, it might simply evaluate this side here and also this side here simultaneously. In that case, when you use -1 over here, you're going to get the contra violation, right? Index out of bound or index too small violation. Yeah, something like that. Okay. Yeah. So now what we can do is to say you will only evaluate this part here when this part here is actually true. That's what we're going to do. So that's why I'm going to say and then. What you're suggesting is another solution. Okay, I'll point it out. Okay. So now there are two fixes to this. Either you can say change that to and then. Okay, as a short circuit corresponding to %% in Java. Okay, or you can do it like that. You can split that into two parts. You can say valid index, and then you would say accounts dot valid index I. Okay, do that first. Followed by, let's say, let me just say balance. Balance condition. In that case, I can say accounts at position I, the balance larger than A. Okay, that will also work. But why would it work?
Because if it fails about the index and it's constant violations,
Post-condition violation, you meant.
also
Oh yeah, precondition, sorry, using require, yes. Yeah. Yeah.
The list of preconditions is short circuit by default.
Yeah, you can think about the way you evaluate a precondition is by going from top to down. You're just going to evaluate one by another. As soon as you encounter the very first precondition violation, you're going to stop there, right? The fact that we put this as first, so that means if this was violated, it's going to stop there. Which means, what if I put it over here?
you have an invalid index, it's going to follow, it won't fail the precondition of balance check, it's going to fail the precondition of the class.
Yeah, you simply, this one here is actually useless in some way, right? Because now, if you simply got -1 as the index, so -1, you'll fail this right away before you even get a chance. Yeah. You mean looping variant and variance? Looping, you mean the example we did in the class, or? Oh, you mean the exercise, right? Okay. Let me just finish this part here. Okay, any question about this part here? Yeah.
So can you quickly summarize what's the wrong with that, balance why you have to use the and then?
Okay, so if you don't have the and then, if you don't have that, the problem is it's no guarantee which part will be evaluated first. So that means that this part here cannot be a guarding condition for that. Okay? So now, if you got and then, it's guaranteed. It's going to be evaluated from left to right. You only evaluate the right-hand side if the left-hand side is actually true.
Oh, so like the y, if it's saying and, then like if I say -1,
Mhm.
it's gonna be saying alpha
Yeah.
with x, like violation. That's why.
Okay, guys, can we keep calm a little bit, please? Okay? Okay. Yeah.
So Professor, I believe you covered something in regards to when you have a precondition, you have to consider it as a disjunction, then you have postconditions, we consider them as conjunctions. Could you kind of clarify that? So I don't know. So I remember when we consider post preconditions, we consider them with respect while having like a disjunction relationship.
Yeah.
And is it
Yeah, basically, whenever you got multiple preconditions or multiple postcondition, when you got multiple ones, it's always going to, like implicitly, it's going to be a conjunction end. Yeah. Yeah. Okay? Yeah.
So the difference between and then is
And then it's a short circuit. And it's like a logical operation where you don't know which bar is going to be evaluated first. They might just be evaluated at the same time.
So that's why using n is not a good idea.
Mm-hmm.
Because if there is a name something on the maps,
Then you will still actually evaluate it right.
right,
Mhm.
and then it's just short.
Yeah.
Maybe it's a little bit of shortcut.
Mm-hmm. Correct.
Shortcut.
Short circuit.
But after you do the practice sample set, you do the as well, and then you go over all the slides, like from the entire course. So you're prepared.
I would say for the practice exam question I gave to you, I would say that one is mainly just to give you the formats, right? Just to get an idea. Well, I said that, right? So I might repeat something from there, I may not. But I'm just saying that one is only for formats, okay? Yeah, I would say when you go over the slides, you want to be very clear about example that we went over, right? To see when we go from one design to another, what's really the reason? Are you able to write it down in writing, right? Like in English, to really express? So yeah, if you can do that for every example we talk about in the class, you should be prepared. To study for the exam. I would say question and answer based formats. You know, I can also post the previous midterm from last year to you, if that might be useful. But again, that one there, I tell you what, that one there just give you another idea about how things can be worked together. I can also post that. Yeah, that's not a problem. Yeah. Again, any example question I posted, don't assume they will just appear on the exam, right? Just give you an idea. But what's the best way to prepare for the exam? You want to show you can really express your ideas about why a design is valid or is not valid. For example, if I just give you post conditions, right? I give you a particular post condition X. Is X appropriate? Number one, yes or no. Second part, if that's appropriate, explain why. If that's not appropriate, explain why not. I'm pretty sure that will be on the exam. Okay. And also for the design pattern, I might say I'll give you a problem that's clearly to be applicable to visitor. In that case, you should be able to answer all the questions related to visitor, like a double dispatch, single choice principle, open close principle, etc. I would say you want to prepare both. Yeah, but you definitely don't have to re-implement a type checker like what you did in a project. No, it's not possible. However, what would be a nice example for you guys to try? Okay, remember the visitor tutorial I supplied, right? That one only did addition multiplication, right? Try to do the following to see if you can do it. Okay. I have an exercise for you guys to try. That'd be a nice one to try. Let's say over here. Let's say for expression over here, right? Let's say under the composite, I got something called sigma. Okay? Sigma, like that, right? Mathematically, you can have different terms. You want to add up expressions together, right? And then, let's make it very easy. So when you got sigma, that simply means you want to add up all the expressions together and get a result. Okay? So now let's say over here, so this one here, maybe you simply got maybe ES, which is an array of expression, for example. So for those of you who already did a tutorial for the visitor, you can just expand your classes a little bit. Okay? And then for the visitor over here, you're going to get visit sigma, for example. And I want you to try how to implement sigma for evaluator. Okay, give it a try. Yeah. But we'll be tolerant on your syntax for the exam, as long as it's reasonable. Mm-hmm. Yeah, sure, no problem. So are we okay with the short circuit? That's what we've been discussing, right? If you're okay with, yeah. Oh, is it a similar question or a different question? Okay, if that's related to it, that's fine. Oh, is there a general way to order your precondition? Good question. Okay. The question was, is there a general way to order your precondition? Okay, let's say this. I would say similar for post condition as well. Okay, you talk about ordering. Require and then P1 and P2, etc. And also ensure P1 and P2. Okay, Q1 and Q2, how about that? I would say in general, first of all, you know that at the runtime, the order of checking the precondition will be P1 followed by P2, right? And also Q1, P1, yeah, P1 followed by P2, and also Q1 followed by Q2. We know that, okay? So that means somehow, if there is dependency amount preconditions, put the least depending first. So what do I mean by that? For example, if I now put AI larger than 0, apparently to really evaluate this particular precondition, it depends on something, which is I is valid. So that means the least depend should be maybe I is valid, maybe I larger than or equal to 0, and also I less than or equal to, for example, count. Something like that, right? So now in this case, you shouldn't put P2 followed by P1. It should be P1 followed by P2. Yeah. Okay. Yeah, I'll just say what kind of dependency? Put the least depend first, and then followed by, right?
Does it really matter? Because they don't have a conjunction relationship. It would just need one of.
Well, apparently over here, you can either put P1 and P2 separately, or you can say P1 and then P2. It's a single precondition, but it might be a little bit too long for you to write, right? So I think separate them out might be nice, right? Correct. Yeah, the O keyword is only used in the post condition. Yes. The O is not used in the precondition. Mm-hmm. No. Okay, you actually asked about, yeah, I wanted to go there. I just want to make sure the current topic is fine, right? Yeah. Okay, so now somehow I think he said first. Let me go to the proof correctness and then go to yours. Okay, yeah. Okay, first of all, I want to make sure you do your parts, right? So now what you should do is, let me just tell you what I want to point out something to you. If you go to the program correctness lecture, okay? Okay, that's for the loops, okay? And that's one example we talk about just to introduce the idea, okay? Make sure you know exactly how the looping variant and variants are evaluated, okay? And then that's the example we went over in the class, right, in detail, okay? That's a looping variance. I would say you can kind of expect in the exam, if you really have no clue about specifying the looping variance, think about how you would specify the post condition, first of all. And the looping variant might just be a special case of that. Okay, what do I mean? Okay, you can see over here, the post condition here is simply say, since we talk about finding a maximum from the input array, so the post condition will just be between the lower and the upper of the array, they are all less than or equal to the result, maximum, right? So now the way you specify the looping variance, presumably you have some array counter to tell you where you are in the scanning process. You want to say, we go all the way from a dot lower until it should be I minus 1, the correct version. And then you want to say result is larger than or equal to what we have seen so far, right? It's a special case. I would say for most cases, you can assume that it's going to be for this course. So we are not really reteaching you 3101. That's something I assume your instructor will take care of that, okay? On the other hand, I want to point out to you this particular exercise over here, okay? This one here. And as you found out, actually there was a small typo over there, okay? So now, this guy here, we are using a loop counter I, okay, integer. And in the body of the loop, there should be I is assigned to I plus 1. I missed that, okay? You should really add it to your code, okay? Otherwise, you will never terminate, right? So now, how can we do the invariance over here, okay? Hints for you. You may want to look at the post condition a little bit. Okay, let's think about what the post condition is saying. Okay, so we got two post conditions over here. The first one is saying every key in the result is actually its corresponding item in the model. So we talk about math model in this case, right? Its corresponding item is simply just V. So that means we have found correct keys only so far, right? The second post condition is to say so all the keys whose corresponding value is V, we have included that in the result. Okay, so that's a post condition. Okay, so now your practice would be to make special cases of this post condition to make your invariance. So which means your loop invariance should contain two parts. Okay, I'll mention that verbally. That's something you should try. Okay, how should the loop invariant look like? I'll just give you one example. For the first post condition here, I'm going to say for every key in the result, which means result I've done so far, right? Its corresponding item should be V. But now you should really go over the result over there, right? Well, like what we have scanned so far. Okay. And what about variance? Any suggestion for the variance? Variance basically measures how many iterations you're going to run for the loop. How many iterations are we going to run? Assuming that we got I is assigned to I plus 1, of course. How do we do that? Well, wouldn't that be very similar to how we did a find max, right? Similar, right? Basically, you have to scan from the beginning until the end, right? In that case, can I simply say, okay, question for you. Can I simply say, let me talk about a variant a little bit, okay? I might just be able to do that, okay? Okay. Okay. Okay, it's here. Okay, so let's talk about the variance. Invariant would be your exercise, okay? Invariance, you want to think about the post condition and make special cases out of that, okay? What about variance?
Variance is supposed to be non-negative or...
Yeah, variance should always be non-negative for sure, okay? Let me give you one suggestion. What if I say, first of all, what about just I? Is that going to be okay variance? Why is that not an okay variance?
It's not useful, it doesn't.
No, I'm just saying which property of variance it violates. Right? What are the necessary properties for a variance? Number one, it should be non-negative. Number two, between iteration, it should be strictly increasing or decreasing. Decreasing. Okay, so now why is I wrong?
It's strictly increasing.
Yeah, it's strictly increasing. Mm-hmm.
So, Professor, on the exam, when we write a contract, what if you give like, not like a valid, but like not a good contract? Like something that's equivalent. Like, I mean, it would pass, but it's not like.
Yeah, exactly. So when I give you contracts, it could be that the contract itself is simply going to compile. It might just even run, but it's simply incomplete. Right? That's something you got to judge. Yeah. Mm-hmm. Well, we'll see. Right? Yeah, so now you should know why I is now appropriate. What about if I say A dot, okay, sorry. Okay, let's say keys, right? How about that? Key star upper minus I. Is that going to be fine? Okay, first of all, okay, you're on the right track for sure. So let me ask you this. If I put key star upper minus I as a variance, are we going to get variant violation? First of all, are we going to? Loop variant violation, are we going to get? The question is, okay, the question is as follows. If I put a variance for this particular loop as key star upper minus I, are we going to get loop variant violation?
Depends on the value of key star lower. It could be negative.
Oh, actually, we assume. Okay, how about, unless otherwise specified, you can always assume the lower for the array is always 1. You can assume that. That's fine.
If when I is equal to key dot upper, then that value is 0.
0 is okay. Ah, you're almost there. You're basically talking about the last iteration, right? Okay, good. So now let me ask you this. If this array is a keys, okay, let's say this is the last index over here. So I, in the last iteration, is going to be set to this value over here, right? At the end of the last iteration, will I be changed again? Are you sure? Well, something that's missing, right? I've said it should be I is assigned to I plus 1. Right, so that means I is going to be incremented by 1. So that means conceptually I is pointing to just outside the array. So now, for example, if upper is simply 10, for example, right? I would just be set to 11. So now if you try key star upper, which is 10, minus 11, that will give you minus 1. So you get loop variant violation. Right? So that tells me this particular variant, which is key star upper minus I, is not good. Right? You see what I mean? So now how do we fix it? Yeah, sure, just plus 1. Yeah, exactly. As easy as that. Plus 1.
Would this be true for across as well?
Typically for the across has to do with the iterator pattern. Usually you don't need any loop counter for your across, so termination is guaranteed.
Right, because sometimes you do across keys dot lower dot keys dot
Oh,
upper.
okay.
And if you're doing that, then
Yeah. So basically like this. So when we talk about correctness condition, or especially termination for loops, right? We are really talking about the from, until, loop, and end. This kind of syntax. Only this kind of syntax we have to worry about termination. Because we learned that this is equivalent to, if you got while some condition over here, right? There's a C family language. So this one also is covered, right? They can be used interchangeably, right? But of course, in the exam, you'll be given this particular syntax. Okay. In this particular case, because you have some Boolean condition over here, so termination is not guaranteed in general. But when you talk about across, okay? Usually when you say across, and then across certain collection C, for example, right? And then you would say is, and then let's say I, for example, okay? And what we said before, implicitly, when I would just be implicitly going to say you're going to call C the new cursor, because you can only use across on C if C is iterable.
which is why when you're doing you say I dot item.
Exactly. Yeah.
It's actually a cursor.
Exactly. Yeah, that's exactly the point. Yes. Yes. Okay. You know what? Let me make it even more explicit for you. If you say S, that's another way to write it, right? If you say I over here, implicitly you basically got I is assigned to C dot new cursor, right? That's an iterator pattern that we talk about, also in lab 2. Okay. So now, usually for the across, we don't have to worry about across for this particular proof correctness. It's usually just guaranteed. Okay. Yeah.
Professor, I didn't understand your argument as to why why we at +1 and why would that be like the previous slide. So when you say the value of index,
Yeah, so the reason that we need +1 is because after the last iteration, I would be incremented to a value that's strictly larger than a the upper, right? And then if you say keys the upper minus I, is going to be negative. That's why I'm going to say +1 over here. Okay, that's why. You need to state the formulation. You need to formulate the proof correctness, or? Oh, okay. Let me say two things. Okay. On the lecture notes, you actually got the following. Okay. Let me just mention that. I'll get to your part for sure. Okay. I'll get there. Okay. So now, if you remember in the lecture, right, we actually got this particular loop over here. So now you got different proof obligation you want to formulate first of all, and you want to prove them. Okay. To prove the maintenance of looping variant, I gave you the solution already. You can go over them. Okay. You can ask me later. Okay. And for others, I also leave them empty in the iPad notes. You can also try to prove them. Okay. How about we prove one of them quickly, and then remember to go back to that particular one. Okay. It'll be similar. Okay, guys. Let's see this particular one. Okay. I'm going to prove it now. Okay. Let's say we got find max. Okay. And then everything has been outlined properly. Okay. So now let's say for the condition, we want to make sure the looping variant is established. Okay. So that means there's no precondition for find max, right? So I'll simply say true. No precondition. And then what's the initialization part for the loop? It's basically in the from part. It's basically I is assigned to lower, followed by result is assigned to AI. Okay. You can see I is assigned to lower, result is assigned to AI. Okay. So now we want to establish the looping variance. And the looping variant is exactly here, right? Okay. So now is everybody okay to say I'm going to formulate this particular condition as a Hoare triple? Okay. So now let's say this. How do we prove that this Hoare triple is true? What will be the two steps that we talked about before? Yeah, find the weakest precondition and then try to see if true implies that. Right? Good. Okay. This one turns out to be quite easy to prove. Okay. Okay, let's do that quickly. Okay. So now how do you prove it? Okay, step number 1. Calculates the WP for, okay, I is assigned to A dot lower, followed by result is assigned to AI. What we want to establish is for every j such that A dot lower less than or equal to j strictly less than I, it is the case. Result larger than or equal to AJ. Okay, WP. Okay? So now, what rule of WP should I apply? Should I apply assignments right away, or should I apply something else? Wow. On the bright side, we still got 2 more review sessions, right? You want to really catch up on this part, right? You don't want to, you know, I'm more than happy to go over detail with you, but I cannot do that on Friday. You know that, right? Okay, okay, good. I'm glad we understand each other. Okay. Okay, now this is your programming part, right? Overall, it's a sequential composition, right? So why don't we apply the sequential composition rule? Okay. So what I would do is I would say it's equal to. Okay, sorry. Okay, so now I'm going to say WP rule on sequential composition. And can anyone here tell me how do I apply that? What's the WP rule? WP S1 followed by S2 to establish R. What would that be? Chelsea. Yeah. Thinking this way. Very good. Good enough. Okay. But you want to formulate it, right? Somehow, I know that upon the termination of S2, I want to establish R. Let's handle that first. What would be the starting states in order for S2 to establish R? You'll be a WP, right? The WP for S2 to establish R. So this will be the weakest precondition right here. Make sure if I can start in a state that will satisfy the weakest precondition for S2 to establish R. Right? That means R can be established. But now we also get S1 before that. So now we want to do another one. We want to make sure that S1 upon termination can really establish this particular WP. That's just another WP calculation. Okay? So what I will do is it's going to be another WP for S1 to establish this. Okay? Again, informally speaking, in order to see what would be the weakest precondition for you to start with so that S1 followed by S2 is going to establish R, what would that be? It's going to be equivalent to the following. It's going to be the WP for S1 to establish something. And that something there is the WP for S2 to establish R. Okay? That's how you think sequentially. Okay? And then if I apply that, okay, what I will do is that's the first part, and this is the second part. Okay? So what I will do is like this. WP for I is assigned to A dot lower followed by result is assigned to, oh, actually, sorry. I forgot to replace that part. Let me do it now. Okay. That one there should be sufficient for you to establish the WP for result is assigned to AI, right? And then, okay, I'll just write it down. For every J such that, just copy verbatim, the lower less than or equal to J, less than I, and then result larger than or equal to AJ, right? So far, we're just unfolding the WP, okay? So now you can see we got rid of sequential composition. So now we can just use assignment rule twice, okay? So what I would do is I'm going to do that now. Okay, so now over here, I can say it's going to equal to WP rule of assignments. Okay, so now how do we apply that? Well, what would be the WP for result is assigned to AI to establish that. You got to replace every free occurrence of something by something. What should we do? Since we're trying to do an assignment over here, so you're going to replace every occurrence of result by AI, right? The only place we got result is over here, right? That's what we're going to do, okay? Okay, so now let me do that, okay? So this part is still there. WP, I is assigned to A dot lower, okay? But this WP can go away because we're going to do the substitution, right? So now every occurrence of result is going to be replaced by AI. So we're going to say for every J such that A dot lower less than or equal to J less than I. It is the case AI larger than or equal to AJ. Okay? Again, you can see now we only got one single assignment left. So now what should we do to get rid of this final WP? Another substitution, right? Okay, so now I'm going to do a little bit lazy here, but that's not something you can do in the exam, okay? Or just for illustration, okay? So now what I will do is this. I know that I'm just going to need another WP, on assignments. So now what should I replace by? I should replace every occurrence of I by A dot lower, right? Good. So that means I'm going to replace this guy here, right? That's not something you should do on the exam. I'm just saving my writing. Replace I by A dot lower. So what do we have now? Eventually, okay, no, sorry, let me write it down. Okay. For every j such that A dot lower less than or equal to j and less than A dot lower. And then it is the case AI larger than or equal to AJ. So that's the green predicate we'll get calculating the WP. What would that be?
True.
I heard true. Why?
Because there's no J that's less than A dot lower, and also.
So that's why I said this case is quite trivial to prove eventually. I want you to look at this. Given that A dot lower is actually 1, okay? Is it possible to find such J so that 1 less than or equal to J and strictly less than 1? Is it possible? Never possible. So that means it's as if we put false over here. And now remember we said before, for every x such that you got false and P of x is always going to be true. Right? That's just some property for your 1090. Just means it is the case. So now this guy here would just be true. So now does true implies true? Yes. Okay, we prove it. Step number 2. Okay, you can see this one here is not that difficult, right? But you need to know the steps well.
So how do we do to enforce this thought this is true? How confused is that?
What I'm saying here is over here. For every x such that I simply got false over here. It is the case property of x. Right? It doesn't matter what P of x is, doesn't matter. Okay, because it's already false, okay, just empty range. So the whole thing will just be true. Right? Questions?
Practice final, there was no rule sheet attached for like rules for it.
Yeah, for WP, as I said before, we're going to give you the WP rule for each one of them. But I don't think you should really refer to them that often. That's not a good sign. Okay, let me go back to your original question, just about stating the proof obligation. Okay, I'll just do one of them. Okay, if you go back to this particular example over here, let's say this. Let's say you're given this particular fragment of code. So here's my question: how do you state all the correctness conditions for the partial correctness and also for the total correctness of this loop, right? So I'll give you one example, okay? So what I would do is I'm going to let me just go there quickly. I hope he's not angry. He might be angry after the exam. Is that a good? Oh, it's not like very common, right? Okay, yeah. Well, frustrated is better than angry, I guess. Right? Anyway. Yeah. All right. Okay. Okay. Back to this particular example here. All right. Basically, let's say you're given this particular loop. Okay. So now what we want you to do is to state all the correctness conditions. For example, one of them, that's some exercise you can do. For example, over here, proof obligation number 1. Proof obligation 1. The initialization establishes the loop invariance. Okay, so that's something that we just did. You want to say, starting from by executing this part of the loop, you're going to establish whatever the invariant it is, assuming that you already come up with the invariant, let's say. Okay, so what you will do is, does this particular feature got any precondition? No. So we simply say true. Okay, no precondition. And then we want to establish whatever invariant it is, right? That's still some exercise you want to do, okay? And what about initialization part? Just simply copy down the code. You will say I is assigned to keys, the lower, followed by creates ks dot make empty. Okay, that's the first one. Okay, let's do one more. Okay, just so you can get an idea. What about another one? Let's say the second one we want to do, proof obligation 2. Let's do usually the more complicated one. Let's say, assuming not ready to exit. Okay, we want to say after the end of iteration, loop invariance is maintained. Okay, that's actually one of the proof obligation we talked about in the last lecture. So that's why, how do we do that? Okay. Yeah. Mm-hmm. Yeah, since we talk about not ready to exit just yet, right? So I'm going to say it is not the case, the exit condition over here. Not the case, I larger than keys the upper. And we can also assume from the previous iteration, the loop invariant was okay to begin with, right? And loop invariance, I'll just say question mark, okay? And then after that, the post condition should be just a loop invariance. Of course, there's a question mark, okay? And now what should be put in here? What should be put? Yep. Should we put this guy here? No, right? We should put exactly over here. Okay? That's something you should put over here. So that's your whole triple. Hopefully, you will just get this kind of question. This kind of question requires your understanding about each of the proof obligation and your ability to actually translate it into whole triple. Okay? So that means given any arbitrary program that involves the loop, you will be at least translate them into whole triple. That might be one part of the questions, and the second part is prove one of them. Okay. Yeah, maybe you want to review a little bit more about the whole triple and correctness issues, and then come back to me maybe not tomorrow, maybe Wednesday. Oh, it's got 2 days. Okay. Are we good? WP is by step, of course. Mm-hmm. Guys, any more questions? Ideally, you can you can still ask me about up to 25 minutes. That's fine. Yes. Yes. Why is it not a whole triple? Oh, good question. Okay. Out of the 5 correctness conditions, only one of them is not a whole triple. It's simply because, let me mention that very in general way. Okay. That's why we said the way you set up the loop invariance should be like a special case for the post condition. Okay. So now let's say this. If you got from something until, okay, invariance over here, okay, you put some loop invariant I, okay, loop invariance. And then until something here, and then loop. Ensure And then here, let's say you got post condition R. Okay, so this is the loop invariance. And this is the post condition. Okay, and then also one thing that's really important is about exit condition. Let me say Boolean B. This is the exit condition. Presumably, the exit condition B here should be some constraint on the loop counter. For example, you might say I should be strictly less than a dot upper, for example, right? So that means when you say the exit condition is actually true, so that means your I is actually sufficiently large, so you have covered the entire array conceptually. Okay. So the proof obligation goes like this. Okay. You want to say proof obligation for this. Upon termination, given that the loop invariance is maintained so far, the post condition is established. Okay, that's actually one of the proof obligation. But this one here, we do not need a loop. We do not need a Hoare triple. Simply means this is to say, since you already terminated, you don't have to execute the body of the loop anymore. That's why there's no implementation there. Okay. So now this one, just to save your time, what we should write is, given that B, the exit condition is now true, and loop invariant I, given that it's implied, right? It's actually it's maintained from the previous one. That one there implies post condition R. Right? This is the only proof obligation that does not require the Hoare triple, simply because we're talking about a case where the loop has terminated, so there's no point to talk about the body of the loop anymore. Right? Okay.
Can I ask a question, like, if you were to take the 4-year version of this course, where we would be dealing with like more rigorous like specification, like more mathematical, like I mean, so like this would tie in, right? So we're using Cal, right? Like
Yeah, I think maybe for this discussion, we'd rather carry that offline. Yeah, it's not really in the scope of this review. Yeah. Okay, any more questions about it? So today we have done basically a little bit of visitor, quite a bit of loop correctness, and a little bit about inheritance, right? Yeah, maybe study more, because the entire thing is covered, right, for all the lecture. Maybe review them. I wouldn't mind if you repeat the question. That's fine. Yes. 4C. Okay. Yeah, give me one moment. I didn't memorize the question, so bear with me. Right? Question 4C. Okay, good. Okay. Improve the design. You mean C, right? Part C. Let me read the question quickly. Okay. Oh, this one is just about the showing the new design, right?
Right, yeah.
What about it?
It says what line we need to change above, like, the code above, and the correct answer from the solution says line 9, or line 8, sorry.
Line.
Line 8 is creating straight.
Oh, I see. Okay, be a typo. Yes, thank you. Yeah. Okay, that's good. So guys, I think what you just mentioned there was absolutely right. So if you go to, let me just point it out. Yeah, good. Let me just go to the solution here. Okay, let me just double check. If you go to the practice question 4C, okay. Yeah, it should be line number, I said somewhere here, right? Can you remind me again where I said it? Oh, over here. Is that line 8 that we talk about?
Yeah, I thought it was
Line 9, yes, I agree with you. Yes. Yeah, this should be line 9. Yes, I agree. All right. Any more questions? Okay, should we call it a day? Not yet. Okay, yes. 5C. Okay, not yet. Okay, let's do a bit one more. Five C, yes, what about it? Ah, good question. Guys, I tell you what, it's a good question here, okay? For those of you who already look at the question here. So here, well, Wuman's question was a good one, okay? When I say names.count equals old, names.count plus 1, okay? Now let me write it down. It's a good question. Although I would expect you to actually answer that, okay? Let me just write one of them. Okay, this one here. Okay, the question was, would it be necessary, for example, to say names dot deep twin dot count equals old names dot deep twin dot count plus 1, for example, right? Just the right hand side, sure. Like that? Okay. Or even that. How about we add a bracket over here? Okay? Okay, so here's the question. The answer is a red. You simply say names.count equals old names.count plus 1. The green one is what you suggested. That one is also correct, but not necessary. Okay? I'll give you a little bit hints. Okay, and then I'll explain it. Think about, well, that's why you want to review the complete post-condition lecture to see how the O keyword is being used. Okay, if I talk about this particular O keyword, it applies to basically this expression over here, right? What's the type for this expression? Integer, okay? Hold that thought. So that means what this will do is it's going to store some integer value only, not really objects, aside in the pre-states. So now if I do anything to modify the names array, is it going to affect the count? Not really. So having deep twin over here is not necessary. Yeah, so let me refer you to that. Okay. Okay, so what you should know, okay, first of all, for this particular example here, you don't have to say names.deep twin, simply because when you say O keyword over here, that one there is going to cache only this particular value, which is integer. Okay, so that means, okay, let me make it even more explicit for you. Let's say the names is referring to this particular array, let's say, and then it's referring to some object over here, right? So now let's say this. If I try this old names.count, so now that means in the pre-states, names.count will just be 4. I'll store 4 aside, just over here, right? Let's say this. If somehow I simply grow the size of the array, that's some malicious post implementation. By growing the size of the array into 5, is it going to affect the value over here? Not really, because that's primitive. It has nothing to do with the structure. On the yeah, that's what I want to say. Okay, so now maybe what you want to review, you can ask me maybe on Wednesday. You may want to look at the complete post-condition lecture quickly. Okay, guys, bear with me. Okay, let's take a few more minutes. Okay, if you go to the complete post-condition lecture over there, Basically, we talk about different versions, remember? You may want to review them quickly. Yeah, okay. I'll show you the ones you should really look at. For example, over here, in version number 3, you can see here we simply say old accounts over here without a deep twin. That's the problem. Because somehow when you say old account, you're only caching the reference to the assigned account. If somehow the account is modified somehow, you will not be able to see it, right? So maybe that's the example you want to look into, okay? Okay, any questions? Well, to see what the problem is for version 1, 2, 3, 4, 5, you may want to go over the slides, and then you can point to me some specific question maybe on Wednesday if you wish. Okay? You mean in the same slides? The solution, okay. Yep. You mean over here? I would say over here I'm using the tilde just because I'm just saying it should be the same name, right? So now using tilde because for the string I want to compare the contents. I think using tilde here is more appropriate because you want to compare the contents. Yeah. Mm-hmm. What I meant was this. What if, let's say this, if you put this guy here to be equal, let's say the reference equality, right? So what that means is, let's say, for example, the names over here, let's say number 3 was used to point to, let's say, Alan. It's a string object, right? So now, let's say the implementation somehow do some reorganizing of the data structure somehow, okay? It simply replace this particular one just by another string that's also of the same content as Alan. As far as we are concerned, this should be okay. It doesn't have to be the same string. As long as the same, yes, as long as the sequence of characters are the same, you're fine. That's what we meant by that. Yeah. Okay, any other quick questions? My general feeling, maybe, you want to study a little bit more, right? But you still got time, before Friday. It's 2 p.m., right? Yeah. Actually, I got 2 exams on the same day, so it's too bad. Questions? I forgot. I think on Wednesday it's 12 to 2. I chose the part that most of you want, right? I'll remind you guys the time. You can also check on the course Moodle. 1B. Okay, how about this last question? Okay, 1B. No, line number 6 over here. Think about what's line 6. It's one of the preconditions, right? Line 8. Oh, I see what you mean. Yeah, there could be another error over here. I see what you mean. Yeah, first of all keywords should not be used in the implementation, number 1. Number 2, maybe there should be a sign equal. Yeah, I agree with you. It should be. Sure. No, the assign equal should be used in the implementation. Yeah. Okay, I'll see you on Wednesday.